Hello, and welcome to another wonderful adventures of the New York City Category Theory Seminar. Today we have Juan Orendain. This is the second time you're speaking, Bass, right?
Yeah, second time.
Second. And he is going to talk about canonical squares in fully faithful equipments. Juan, but you can't assume that we were all here last time. So, okay, take it away. Hold on, let me make you go.
Yeah, well, thank you very much, Nason. I'm very excited to be here for a second time. Last time I was here, was it about 2 years ago? I talked about this program on double categories and bicategories and this thing I called the length. And I told you about this conjecture that I had on frame bicategories on our core equipment. So this is part of that same program. So I recently moved to Case Western to Cleveland, and well, that of course takes a little bit of it takes a bit of time to adapt. So it took a bit of time to get that going again. But yeah, so we have a couple of results on this, and just wanted to tell you about it. So I'll be dividing the talk into the following 4 parts. So I'll first talk about globularly generated double categories. Then I'll talk about length in equipments. Then I'll talk about π-indexings and cross products. And then I will say a bit about length of fully faithful equipments. So I'll tell you what that is in a second. But first, let me tell you what globularly generated double categories are. So yeah, I'll consider basically 3 models for 2-dimensional categorical structures. The first is bicategories. So bicategories are categories enriched over the 2 category of categories functors and natural transformations. So they're what you already know. So objects, 1 cells and 2 cells, and you have 2 directions which you can compose. So this is, I would argue, the most common 2-dimensional categorical structure. Usually if you have a sort of object, a morphism, a type of morphism between these objects and a morphism between these morphisms, then you have yourself a 2-category or a bicategory. The game you play when you work in bicategories is the game of pasting diagrams. And the shapes of your 2 morphisms or 2 cells are either globular or equivalently kind of simplicial. And so bicategories are very well studied, and they've been around for a very long time, and very important people have done very important things on them, and they're pretty well understood in some sense. Now, the other type of 2-dimensional categorical structure one considers is double categories. So double categories are categories internal to cat, as opposed to bicategories that are enriched. Double categories are also pretty common, a little less so than bicategories, I guess, but now they're having this renaissance where a lot of people are considering their structures as being organized into double categories, but they are also pretty common. When you play the game of double categories, you play the game of subdivisions of squares instead of pasting diagrams, which is a bit different, but it's basically the same idea. The shapes of your square, the shapes of your 2 cells now are squares and not globes. So that makes the theory a little bit different. It gives it a little bit of a different flavor. So we have bicategories and double categories.
Can I just say something? To me, it's interesting. Strict 2 categories don't even come into this.
No, so here I'm talking, when I talk about bicategories, I'm including 2 categories. I'm ignoring strictification and coherence and everything. So I would include 2 categories in the bicategory part. And double categories, I'm talking about them in the most, so I'm talking about them being quasi-double categories or double categories, strict double categories. So I'm ignoring all
coherence questions.
Yeah. All right.
Just one more thing. Your framed bicategories are somewhere in between these 2?
Yes, exactly. Yeah, so frame bicategories are kind of in between. They're this thing, they're not quite, they're bicategories with a little bit more, and they're also double categories with a little bit more, but that little bit more makes them be kind of like bicategories. So frame bicategories, yes, exactly. They're in between. You can
okay, but I don't know
them.
how to think of a double category as a type of bicategory. You know, in other words, okay, go ahead.
Yeah. So I'll explain that in a second. Basically, the idea is that a double category, the shape of a two cell in a double category is a square, but a type of square where you have like a canonical square, a Cartesian square, and a globular square. So they're basically, you can split every square into a collection of squares that you can control and a globular square. So they're almost kind of like a two category. The two cells are almost, or you can think of them as being simplisher or globular plus a canonical square. In that sense, they're kind of like bicategories. But I'll explain that a little bit more in a second.
Okay.
I'll just say that for now, yeah, the way you should think of frame bicategories, exactly as you said, Noson, you have to think of them as something in between bicategories and double categories. You can think of them as a two category with some extra condition or structure. That's the way people that do equipments think about them. There are two categories together with some pro-arrows. That would be an extra bicategory that sort of enriches the two category. Or you can think of them as double categories with also some extra condition. That would be the condition that the horizontal domain and codomain form a fibration. And so, yeah, as I was saying, the shapes of two cells are particular squares and globes. So, yeah, very much in between the two structures. So there are very well established relations between the three types of structures. Bicategories can be thought of as special types of double categories, and double categories can be made into bicategories. You can horizontalize them. I'll explain this a little bit more in a minute. This is very well understood, and it has a very nice structure. Frame bicategories, same thing. Bicategories, you can think of them as frame bicategories, and frame bicategories, you can always like squeeze them or squash them into bicategories. Double categories and frame bicategories is less clear what their relation is. So frame bicategories are double categories, but can every double category be made into a frame bicategory? Yeah, that's a different question. Now, the goal of this program is to understand the relation between these three things in a bit of a deeper level, especially the relation between bicategories and double categories, but frame bicategories are sort of play a very important role. So yes, I was saying we want to represent the two cells of a double category as a square. So here, phi is a square. The vertices are A, B, C, and D, so the objects of the square. So this phi would be a square from alpha to beta. So we read squares from top to bottom and from left to right. So we would call alpha the domain of phi, beta the codomain of phi, F the left frame of phi, and G the right frame of G. All right. Now, usually identities are represented as long equal signs, but we'll represent them as red arrows. So, for example, horizontal identity squares or unit squares are squares that look like this. So you have a morphism, a vertical morphism F. Then the unit square of F will be a square of this form. So this would mean that the top and bottom arrows are identities. Okay, so this is a very important class of squares. This is the identity with respect to composition, horizontal composition. So you compose the squares horizontally, you put them together, and vertically. So another important class of squares is the squares, the class of the squares that have red boundaries. So these are squares where left and right frame and domain and codomain are identities. So these you can think of as kind of like spheres in your double category. So we'll write pi2 c comma a for the set of all squares with red boundary and where all the vertices are the vertex A. So this is kind of like a second fundamental group of the double category on the vertex A. So by the Ekman-Hilton argument, this is a commutative monoid. So horizontal composition and vertical composition are both the same, and they're commutative, so we just consider this as a commutative monoid with that operation. Now, globular squares are the squares that have this form here at the bottom. So squares where the left and right frame are identities. So if you think that you can identify a red arrow into, collapse that into a point, then this would have the shape of a cell in a 2 category as a globe. Now the collection of globular squares in a double category forms a bicategory. We denote that as HC. We call this the horizontal bicategory of the double category C. And so in this way, we can associate to every double category a bicategory. We just consider its horizontal bicategory. And now every bicategory can be considered as a double category where the 2 cells are just the squares of these form. So yeah, in this sense, every square of this form contains, so squares of this form are the globular squares, and the globular squares are contain all the bicategorical information of the double category or something like this. Oh, sorry. All right.
So, one second. Go back. So if the vertical lines are red, it becomes a bicategory, a horizontal bicategory. And if the vertical lines are, I'm sorry, if the red lines are horizontal, then it's what? Does it anything?
So do you mean like the top up? Yeah, that would be a bicategory as well. So that's called the vertical bicategory.
Okay, so
yeah.
So you have these bicategories sitting inside this.
Yes, exactly.
Double categories.
Yeah. So we usually, I'm not sure. Well, it depends on the author. Some people sort of prefer the horizontal direction to do all the interesting stuff. Some people do it vertically. But yeah, so we'll just consider horizontal. The way you sort of make a double category into a bicategory is, for us, horizontal, but you can do it vertically as well.
The main point is if you pinch the red lines, you get globular. You went from square to globular.
Exactly. Yeah.
Okay, good.
All right. Now, all right. So I'll call a declaration of a bicategory. Now we just consider a bicategory. So a double category with pinch left and right edges. So suppose B is a bicategory, then a declaration for B will be a collection of arrows, well, a category, B star, having the same collection as of objects as B. So if B star is a declaration of a bicategory B, then we'll say that B star comma B is a decorated bicategory. That's another type of 2 categorical structure. So a bicategory together with a collection of arrows or a category of arrows between the objects of the bicategory. Now, suppose C is a double category, then the pair formed by the vertical arrows, which we call C naught here, and the horizontal bicategory of the double category, that would be a decorated bicategory. So the thing on the right would be a bicategory, and the thing on the left will be a category, and the objects will be the same, right? So we'll write this as H star C, and we'll call this the decorated horizontalization of C. So what H star C does is basically the same thing as H, C, it just remembers the vertical arrows, but that's it, right? So we're interested in the following problem. So we're interested in, suppose B star comma B is a decorated bicategory. Now, we know that if B is a bicategory, we can think of B as a double category with red vertical arrows. Suppose you have a bicategory B, you have a collection of possibly vertical arrows. Now the question is, can you find a double category having B as globular squares, but having your collection of vertical arrows as vertical arrows? So if B star comma B is a decorated bicategory, we want to find double categories C satisfying this equation, H star C equals B star comma B. In that case, we'll say that C is an internalization of B star comma B. So internalization in the sense that double categories are categories internal to CAD and bicategories are enriched over CAD. So yeah, what I'm asking here is, suppose you have a bicategory B, so a collection of globular squares like this, and suppose you have a collection of vertical arrows and you want to where the vertices of the vertical arrows are and the squares are the same. And what I'm asking for is, so with this structure, with the horizontal arrows of the squares and the vertical arrows, I can form a bunch of hollow squares like this, and I'm asking for ways of filling those squares, finding a collection of solid squares. So in a way that they form a double category, where the globular squares are the original globular squares that we started with. Okay, that's, yeah, very pictorially the thing that I want to do. So some examples.
It has a feel of a quasi-category. You're trying to fill in the horns in some sense.
Yeah, in a sense, yeah. I'm trying to fill, exactly, yeah. Which is it's kind of also, as we'll see, what you do in frame by categories. So yeah, I'm trying to get some information, get some sort of hollow things, some kinds of horns. I'm trying to fill them with some sort of fixed data that I want. So for example, if you start with a 2-category B in the first example, you have a category of 1 cells. So you can consider that decorated by category B together with its 1 cells. Then you can internalize that using quintets, the quintets double category construction. So that's pretty classic. So you can consider every bicategory as a double category in this sort of very vertically trivial way. Now quintets does the same thing if you decorate your 2-category with the 1 cells of the 2-category. Now, if you consider the bicategory of adjunctions and you decorate it by functors, then there is a double category of adjunctions. That would be an internalization. So the same thing for span. So you have a bicategory of spans. So the classic structure, you decorate it by functions, then there is a double category of spans that internalizes it. Same thing for profunctors, bimodules, etc. So this is sort of a classic thing. I haven't explained why I would be interested in this, but this sort of happens a lot. So you have a bicategory and a special collection of vertical arrows, and then there is a double category that solves this problem of sort of filling the squares. So, well, one thing that's very interesting about this, that I think it's sort of interesting, is that we don't know if all decorated bicategories can be internalized. So you can come up with sort of pathological examples that you could imagine that you wouldn't be able to internalize. But in this last example, so we had algebras and bimodules. So you have a bicategory of bimodules. Objects are algebras. Morphisms or 1 cells are bimodules, and 2 cells are bimodule morphisms. So if you want to consider sort of morphisms between algebras as part of your structure, then you internalize that into a double category where the vertical arrows of the squares are morphisms of algebras, and the things in the middle, the fillers, are sort of equivariant morphisms with respect to the vertical arrows. So you'd expect the same thing to happen for every reasonable sort of algebra. Now there is this, or there was, a program related to the Stolzenteigner conjecture that there was a structures called conformal nets that were based on von Neumann algebras, which are not really well behaved, but you can make them kind of behave like usual algebras. And so one of the problems in the area was you have von Neumann algebras, you can organize their bimodules, their whatever, something, Hilbert bimodules. They form a bicategory. There is sort of like, it sort of behaves like the example of algebras and bimodules. And you would want, for some reason that I'll talk about a little bit later, to make this into a double category. But it turns out that it's very difficult to know if you can do that. So you can't always do this. It seems like you should always be able to do it, but it's not always known. And even if it is known how to do it, it's not always clear that you have a sort of like a canonical way of doing this, as you do in all these examples. So this is sort of an interesting relation between bicategories and double categories. Once you take into account the vertical arrows, it's like things become a little bit more complicated. Yeah, so this is where globularly generated double categories come in. So a double category C is globularly generated if C is generated as a double category by its collections of globular squares. So what I mean by that is that a globularly generated double category is a double category where every square can be written as a vertical and horizontal composition, or mean, can be subdivided into globular squares and horizontal identity squares, so squares of this form. So you can have a very complicated subdivision of your square, but all the squares involved in the subdivision will be sort of a bicategory nature, will be either globular or horizontal identities. So, well, not every double category is globularly generated, but every double category contains a globularly generated double category canonically. So if we write gamma C for the sub-double category of a double category C generated by these squares, by horizontal identities and globular squares, then gamma C we call the globularly generated piece of C. Gamma C is globularly generated, number one, and number two, the decorated horizontalization C is equal to the decorated horizontalization of gamma C, number one, number two, and number three, gamma C is contained in every other subdouble category D of C having the same decorated horizontalization of C. So what this says is that this gamma C, this globularly generated thing, solves the problem of internalization for the decorated horizontalization of C in a minimal way inside C. So H star of gamma C is the same as H star C, and gamma C is the minimal sub-double category of C satisfying that condition. So what this says is that globularly generated double categories are minimal solutions to this problem of internalization of filling squares with this sort of condition that you take into account the vertical arrows. So a decorated bicategory, B star comma B, admits an internalization if and only if admits a globularly generated internalization. So if you want to solve this problem, if you have a decorated bicategory and you ask the question, well, does there exist a double category internalizing it? And you don't know, well, it would be exactly the same question as asking if does there exist a globularly generated internalization of that decorated bicategory. That might not seem like much, but globularly generated double categories, as we'll see, you can like put your finger on them. You can describe them very easily. They're sort of very small. And so this way of thinking of internalization is just something that you can actually like describe in terms of generators and relations. So that relation can be described in terms of this diagram here, which I don't think I want to explain, but this just says that globularly generated double categories sit in sort of a special way inside double categories. Yeah. All right, so that was globularly generated double categories. Now let me tell you about length and equipments. So the length of a double category is a measure of complexity on the squares of the globularly generated piece of the double category. So as I just mentioned, the globularly generated piece, this gamma C, is sort of a very important part of a double category C if you're interested in understanding how to reconstruct C from its decorated bicategory, decorated horizontalization. And so we have a number that describes how much work do you have to do to construct this gamma C from the decorated horizontalization of C. So, but this has a very nice pictorial description. So suppose you have a double category C, globularly generated. You take the view that you already, like the theory of bicategories and decorated bicategories, you understand very well. That's trivial for you. So if you know a bicategory, then you know everything you need to know. You want to understand now the more complicated double categories, let's say. And so if C is a double category, let's say a globular square or a horizontal identity square, you mark as a zero complexity. These are very easy. You understand them very well. Now, if a square, you can write it as a vertical composition of squares marked with a zero. So a vertical composition of very easy squares. And it's not marked with zero. It's not horizontal. It's not a globular square nor a horizontal identity. Then you say that square is of length 1. So square of length 1 is just a square that looks like this. It's a vertical composition of 0 marked squares. Now, given horizontal, so suppose phi and C are squares of length 1, and they're horizontally composable. it might be the case that you can find vertical subdivisions of phi MC such that the horizontal composition of phi MC looks like this. So the decompositions, you can find decompositions of phi MC into squares of length 0 or complexity 0, where the squares match horizontally. In that case, using the exchange relation or the Ekman-Hilton argument, you can first compose the first two complexity 0 squares into a complexity 0 square, then the second, etc., compose all of them. And then your square would be a vertical composition of squares marked with a 0. And so your square would be of length 1. That would be the idea. So if given two squares of length 1, you can find decompositions like this that match horizontally, then the horizontal composition is of length 1, right?
Can I ask you a question?
Yep.
If I take a set of objects and I generate the group over it, right? So then I have a group. So, but it's not clear that you can define this length operation. In other words, there might be different ways of describing every element of the group. From generators. Why don't you have that problem?
No, I do have that problem. This depends on a specific way of writing a subdivision of a square. So the idea here is that you have a very obvious way of, you have generators, your globular squares and your horizontal identities, and you have a very obvious way of generating every square of every globularly generated square. So you consider all the squares that can be written as a vertical composition of globular squares and horizontal identity squares. Then you consider horizontal compositions of those, then vertical compositions of those, then horizontal compositions of those, etc. Right? That would be, you start under the assumption that that's the sort of algorithm that you'll follow, which is, in the case of groups, you don't have a direction in which you compose a preferred direction in which to compose or to multiply elements of a group.
Right.
But yeah, so here you do have this, you choose vertical and then horizontal and then vertical and horizontal. And then all I'm saying here is, if you choose vertical first, then okay, that will be one direction. And then if you compose horizontal, then you'll have two directions. If you can make that into a single vertical composition, then you'll say length 1. So the length here is not the number of squares of marked with a 0, but the number of directions that you'll take. So if you just have one vertical composition, no matter how many of those you have, you'll say that it is of length 0. So for example, if you have two squares of length 1 you can't find length 1 decompositions that match horizontally, then this horizontal composition, you can't describe it as a vertical composition of squares marked with a 0. Then you'll say this is of length 2. So it's not the number of squares, but the number of times you have to do the operation. Yeah, that's
I understand. Thank you.
Yeah. All right. So this is length 2. So length 1 is easy in the sense that you only have to do one direction. Then you have length 2, then length 3, then length 4, etc. In some double categories, you can reduce everything at the level of length 1. Sometimes you can reduce everything at length 2, etc. And so you have this measure of complexity for squares, and you define the length of a double category to be the supremum over all the lengths of the squares, over all the complexities of this decompositions of globularly generated squares. All right, so for example, in these examples that we talked about, quintets, adjoint pairs, spans, profunctors, bimodules, and now the double categories of vorticings all have length 1. So if you have two squares of length 1, two length 1 squares, you can always find a subdivision where if they're horizontally composable, then the subdivisions will match and the horizontal composition will also be of length 1. All right. Now, there are examples of double categories of arbitrary length and of infinite length. But yeah, so what do these examples have in common? Well, what they have in common is that they're all equipments or framed by categories. And so, yeah, I'll tell you what that is, but obviously the conjecture here would be that all equipments have length 1. Okay, now a frame by category is, as you pointed out, a double category with a condition of sort of this quasi-category, this sort of form filler condition. So, so an equipment is a frame by category where the left and right frame, so this is L times R, the functor that associates to every square the pair formed by its left arrow and its right arrow, that is a bifibration, so a fibration and an off fibration. What that means is that if you have your double category and you have a niche like this, so you have a horizontal arrow alpha and 2 vertical arrows F and G that look like this, then you can fill this with a Cartesian square. Now, what does it mean for this square to be Cartesian? That means that if you have any square like this, so you have your niche alpha, and then you have F and G, and then you compose that with morphisms H and K, then you can decompose the square as a square of this form. So the Cartesian square on FG alpha, now composed with another square with left and right frames H and K. And so this decomposition is unique.
So this is the fibration. It's not just onto, but it's nicely onto.
Yeah, exactly. So yeah, it's very nicely. So the decomposition is unique. So yeah, pretty nice. And now what this gives you is what we mentioned before. So if you have a square like this, so you can write this as, so the left and right arrows, you can write them as F followed by an identity and G followed by an identity. And so this, you can write it uniquely as a Cartesian square on the niche having this phi followed by a globular square uniquely. So yeah, as we mentioned before, in a double category, every square can be written as a globular square followed by a special square or Cartesian square. So not quite globular, because every square is kind of globular, except for a Cartesian square, for a special square. All right, now there are a couple of things to say about equipments. They give you a restriction and an extension operation of scalars along vertical arrows. So basically, if you have an arrow alpha and you have F and G morphisms, the top arrow of the Cartesian square, you think of it as the restriction of alpha along F and G. Now the up fibration part will start with a niche where the alpha is on top. Then you get a bottom arrow, and that will be the extension of alpha along F and G. So that's basically what a frame by category will give you. Yeah, so frame by categories or equipments are sort of the preferred 2-dimensional categorical structure for doing formal category theory. So if you want to have like a proper Ionetta embedding theorem, we need, in some sense, some formulations, you need a restriction of profunctors. And then, so this sort of restriction along vertical arrows gives you a nice way to talk about this in a frame by category, which you don't have in a bicategory or in a 2-category. It gives you a natural way of defining 2-dimensional symmetric monoidal structures. So it turns out the symmetric monoidal bicategory is, it's its own thing, and it's very nice and everything, but sometimes it's just like too difficult for the purposes of if you're doing algebra and you want your bicategory of algebras of whatever sort to be a symmetric monoidal bicategory, then the usual definition of a symmetric monoidal bicategory is just completely inefficient and unnatural. And so sometimes, and this is sort of championed by Mike Shulman, it's better to extend that into a frame bicategory. Symmetric monoidal structures and frame bicategories are way more natural. The coherence equations are defined in terms of the vertical arrows. And so you define a symmetric monoidal structure there. And if the double category is a frame bicategory, then that will, under horizontalization, go down to a symmetric monoidal structure in the horizontal bicategory. And if you do like homotopy theory, then yeah, frame bicategory will have a folding operation. So it will give you thin squares in the sense of like strict homotopy theory, in the sense of like Ronnie Brown and all of those people. All right, so yeah, frame bicategories are good, are nice. So yeah, we have this conjecture. So if C is a frame bicategory, then the length of C is equal to 1. Now, if this is true, and we want it to be true, is, well, if you start with a decorated bicategory, suppose you want to lift it or internalize it into a frame bicategory, then you can break your problem into the following 2 steps. So first, you decide if you can internalize your decorated bicategory into a globularly generated double category of length 1. That is a problem, an easier problem. And then you can decide, given a double category, globularly generated double category of length 1, if that is the globularly generated piece of a frame bicategory, also easier. So yeah, that breaks the problem of deciding if a decorated bicategory is can be extended to a frame bicategory into 2 sort of more manageable steps. So we do want this conjecture to be true. All right, now, how do we prove that a double category has length 1? That's what all this pi2 indexing stuff is all about. So we have this lemma that I proved in, I believe, like 2019 or something, that says the following. So in a globularly generated double category, if you have a square like this, of length 1, if the square is of length 1, then you can decompose it in a very particular way. So C can be written as a vertical composition. Well, this doesn't say much. Now, there is a vertical composition like this, where you have one special square with a upwards arrow, and a final square with a downwards arrow. And then you have a vertical composition of alternate types, an alternating sequence of 2 types of squares. So you got the P's and you got the UIs. So here, the first and final squares, so remember, this is the shape of your square that you're trying to decompose, length 1. The first square is sort of a square that looks like this. So it has the same top arrow as your original square, and every other arrow is red. The bottom square has the same bottom arrow as your original square, but every other arrow is red. Now the UIs here are all horizontal identities, and the CIs are all red boundary squares. So every square of length 1 can be decomposed as first a square of this top left form, then a vertical composition of horizontal identities and red boundary squares, and then at the bottom you would have a downwards arrow square of this form here. So you have like a bottom, you can think of this as sort of like the sandwich. You would have a top bond, phi top upwards arrow, a bottom bond, and then some sort of meat in the middle where you have a vertical composition of UIs and CIs, where the UIs are horizontal identities and the CIs are red boundary squares. So yeah, you have top square, bottom square, and in the middle, a vertical composition of UIs and CIs. Yeah, so every square of length 1 can be described like this. And if we want a double category to be of length 1, then we want horizontal composition of squares of length 1 to be, again, of length 1. All right, now the simplest possible form of a decomposition like this would be to have the thing in the middle have just one square, one horizontal identity. So would be something like this. So this would be the simplest possible length 1 form of a length 1 decomposition of a length 1 square. So obviously not every square of length 1 in any double category admits a decomposition like this, but when it does, we call it a canonical square. So the canonical squares in the title of the talk are squares in a double category that can be written like this. A top square of this form, horizontal identity, and the bottom bond square of this form. And a decomposition like this, we call it a canonical decomposition of the canonical square. Now we have this very nice lemma. If C is a double category, then if every non-globular square phi of C of length 1 admits a canonical decomposition, then the length of C is equal to 1. So if every square of length 1 admits a canonical decomposition, or is a canonical square, then the double category is of length 1. Now, how does this argument go? Well, suppose you have phi and psi, two length 1 squares. By this assumption that every length 1 square admits a canonical decomposition, you just take the canonical decompositions, compose them horizontally, and you just observe that this decomposition, this composition is this composition here, which is, of course, it's a canonical square, and canonical squares are of length 1. So basically, if you assume that every length 1 square is canonical, you observe that horizontal composition of canonical squares is canonical, and canonical squares are of length 1, then horizontal composition of length 1 squares is again of length 1, and the double category is of length 1, which is pretty nice. All right, so again, we're in the business of proving that a double category is of length 1. So we have a strategy for proving that a double category is of length 1. So we want to prove that every square of length 1 is a canonical square. All right, how do we do that? Well, we want to turn every length 1. Well, at least one possibility would be to try to turn every length 1 decomposition of a square of length 1 into a canonical decomposition, right? So we're given a square of length 1. Somehow we want to shuffle all the squares in this length 1 decomposition, this thing with the top bond, bottom bond, and stuff in the middle, to reshuffle the stuff in the middle in such a way that we get a canonical decomposition. So that would boil down to the thing in the middle in a length 1 decomposition of a length 1 square is a vertical composition of things like this: a red boundary square followed by a horizontal identity square. If baked into the definition of our double category, we had a structure that would allow us to slide down a red boundary square from a horizontal identity square. So substitute this square here by a square of this form. So the bottom red boundary square would be different, but it wouldn't matter. So you could move it down the horizontal identity square. Then if we had a decomposition like this, so we would have a bunch of compositions as the ones that I mentioned, and you could start sliding down red boundary squares down horizontal identities. You could just do that as many times as you need, and then you would have on top a vertical composition of horizontal identities, so horizontal identity. At the bottom, you would have a square that looked like this, a red boundary square, the vertical composition of all the leftover red boundary squares that you had. And then you just observe that the thing at the bottom, the theta, composed with a phi downwards arrow, is a bottom bond type square. And so this would be a canonical square. And so if we had a technology that would tell us, you have your double category C. In C, you can slide red boundary squares down horizontal identity squares, then every length 1 square would be canonical, and then our double category would be of length 1. So yeah, we kind of want to look for that. Also, if the same thing you can say if you can slide red boundary squares up horizontal identity squares. So what kind of structure allows us to do that? Well, there's this thing that we came up with called π-indexing. So I say we because this I wrote with my PhD student, Ruben Maldonado, which I don't think is in the audience, but yeah, he worked on this. So we started with, so for now I was talking about, you have a double category. What would be the kind of structure that would allow us to slide red boundary squares up and down, up or down, horizontal identity squares. Now, suppose you have, that would depend only on red boundary squares, which are globular. So those depend only on the decorated horizontalization of the double category, and horizontal identity squares, which only depend on the vertical arrows. So this sort of technology that would allow us to slide red boundary squares up and down horizontal identities, in principle, should only depend on the decorated horizontalization of the double category. And so we worked on defining exactly what the structure would be on a decorated bicategory. And if we start with a decorated bicategory with this structure, that I'll just tell you what that is, then we should be able to reconstruct a double category where every square is canonical. All right, so this kind of structure is a π2 indexing. So suppose B star comma B is a decorated 2 category or a decorated bicategory. Then a π2 indexing on B star comma B is a functor phi from the decoration B star to commutative monoids, such that for every object of B star, phi of that object is the commutative monoid π2 of B comma A. And, well, obviously, if you have a morphism, let's say from A to B, then phi of that morphism will be a morphism of commutative monoids from P2, π2 of the first object into π2 of the second object. Now, π2 of indexing is the same thing, just you consider the opposite category of the decoration. Right? So, for example, if you have A an abelian group, G a group, then you can associate to that a decorated bicategory. So omega G would be the looping groupoid of G. So that would be the category with a single object, and G as its groupoid group of morphisms. And 2 omega A would be the double looping of A. So 2 category with a single object, single 1 cell, and A as its 2 cells. Then a π2 indexing on this is actually an action by automorphisms of G on A. And a π2 of indexing is just an action by automorphisms of G on A, right? So that's the sort of intuition. These are kind of like actions by automorphisms defined on the decorated bicategory. Okay. Now, our main theorem about π2 indexing says that if B star comma B is a decorated bicategory, then for every π2 indexing or every π2 up indexing, phi on B star comma B, then we can associate to that a double category that is number 1, globularly generated, number 2, internalizes our B star comma B, and number 3 is of length 1. We call this the cross product of B star comma B with respect to phi, and we'll write it like this. So yeah, what we do is basically, well, we're trying to sort of re-engineer this idea of having a canonical such that, well, having this structure that would allow for every length 1 square to be a canonical square. So we definitely want to construct the cross product of B and B star by, so we want to make every square to be canonical. So what we do is we have the data of B star comma B. So we have the top and bottom squares. So those live inside B. So we have them when we have B star comma B. And we have vertical morphisms, which are the morphisms in B star. So we can just say, consider the formal unit square on a morphism F. And then we can compose them formally. And we can say, okay, we want those to be the squares of our double category. Well, now we have to define the operations. We have to define horizontal composition and vertical composition. Now, horizontal composition, as we saw, I mean, canonical squares, the thing about them is that the horizontal composition of canonical squares is again canonical. So we just define the horizontal composition in that way. So if we have 2 canonical squares, formal canonical squares here, their horizontal composition is just composing the top squares, the bottom squares, and just leaving the horizontal identity fixed. And the vertical composition would be this drawing that I have here, this horrible drawing. So you have 2 canonical decomposition squares here, 1 at the bottom, the first 3 squares, and then 1 at the top. Then you compose them vertically, like by stacking them together, and then you would have a top square, bottom square, and in the middle you would have 2 horizontal identities and of this vertical composition of bottom and top squares. Now the vertical composition would be a red boundary square, and you can slide that down or up depending on if you have a π2 indexing or π2 up indexing, and then you make that into a canonical square. And then, well, you get a double category, you get horizontal composition and vertical composition, and you get this sort of sliding up and down operation. And so every length 1 square is a canonical square, and we get an internalization of length 1. There is some representability questions here, but I think I'll skip that. So as an example, if G is a group and A is an abelian group, so as I mentioned, we have this decorated bicategory omega G to omega A, then if phi is a π2 indexing, this is what this is saying, then that would be an action by automorphisms of G on A. Then the bicategory, the cross product of 2 omega A, comma, omega G by phi, that would, you can write things down and you can see that you can identify every square in that double category with a square like this. So something where the top and bottom arrows are red, you would have a left and right arrow, you would decorate that with elements of G, and then the square you would decorate with an element of A. And then you can prove that the vertical composition of squares like this is precisely the composition in the semi-direct product of A by G with respect to this action by automorphism. So yeah, the intuition is that this cross product is really a semi-direct product. All right, now, yeah, fully faithful equipments. So yeah, we have this definition. So suppose C is a frame by category. Suppose F is a vertical morphism, so a vertical arrow. We'll say that F is fully faithful if the horizontal identity square of F is Cartesian. So C is a frame by category, so you always have Cartesian squares. And we'll say that F is absolutely dense if the horizontal identity square of F is up Cartesian. So we'll say that the double category C is fully faithful or absolutely dense if every vertical arrow is either fully faithful or absolutely dense. All right, what do we get in a fully faithful frame by category? Well, this is a frame by category, and all we have is that we get a special choice of Cartesian squares or up Cartesian squares for certain niches. So what we have is that if we have a square like this where the bottom is red and the left and right arrows have a single F as the first morphism in the composition, then you can decompose this, the square of this form, as a square at the bottom, so a horizontal identity square followed by some square with left and right arrows H and K. So more importantly, if you have a square of this form, phi, where the bottom is red and left and right arrows are a single F, then you can decompose that uniquely as a horizontal identity square on F and a top bond type square, so a globular square. All right. So we'll leverage this to associate to every fully faithful double category a pi2 up-indexing. All right, so these, this is important. So in the double category of profunctors, in the frame by category of profunctors, a functor, a vertical arrow, is fully faithful if and only if as a functor is fully faithful, and is absolutely dense if and only if as a functor is absolutely dense, so surjective on objects. In span, in the double frame by category of spans, a function, so a vertical morphism, is fully faithful or absolutely dense if and only if it is an injective function or a surjective function, respectively. And the same thing happens for the double category of relations. So prof, span, and rel are not fully faithful, nor is the frame by category of bimodules. But I mean, here I have, okay, so if C is a frame by category, every vertical isomorphism, every vertical arrow that is an isomorphism is fully faithful and absolutely dense. So if the category of vertical arrows of a double category is a groupoid, then the double category is, or the frame by category is fully faithful and absolutely dense. And we can associate for every double category is for every frame by category is sub frame by category, C star, formed by every square such that the left and right arrows are isomorphisms. And that will always be fully faithful and absolutely dense. So for example, prof star, span star, and rel star, those would be fully faithful and absolutely dense frame by categories. Also, the frame by category of Bordisms is fully faithful and absolutely dense. So road continues here, but it's dense. Also, there is another, you can also consider for a frame by category C, you can consider the collection of all the squares such that the left and right arrows are fully faithful or absolutely dense. That will be a fully faithful or absolutely dense sub-frame bicategory, and that will satisfy a very nice universal property. And you can always do that for every double category. So that will give you a bunch of examples of fully faithful and absolutely dense frame bicategories. Now, okay, why do we care about this fully faithful and absolutely dense stuff? So if C is a fully faithful frame bicategory, and F is a vertical morphism, and phi is a red boundary square on the codomain of F, then we can consider this square here. So we have F, the morphism from A to B, a vertical morphism. So we just consider the horizontal identity on F. And then we consider phi, a red boundary square on the codomain of F. Now, since we're assuming that C is fully faithful, then the Cartesian condition, the fact that the horizontal identity on F is Cartesian, will give us a unique decomposition of this square here of this form. So give us a decomposition of this square here as the horizontal identity of F followed by another red boundary square, which we'll call phi F of phi. So for every red boundary square on B, where F is a morphism from A to B, we can associate a new red boundary square now on A, the domain of F. And so we showed that this assignment, so the assignment that associates to every object in the decorated horizontalization of C, it's π2 commutative monoid of in A, and to every morphism F, the function that associates to every red boundary square like this, the top red boundary square here, given by the Cartesian decomposition, then that would be in π2 of indexing. Now, if we assume that C is, instead of fully faithful, absolutely dense, then we will get π2 indexing using the same method. So we can associate for every fully faithful double category, we can extract from that a π2 of indexing. And for every absolutely dense frame bicategory, we can extract from that a π2 indexing. And yeah, well, there is an example here, but I won't go into that. Now our main theorem on this, and this is, yeah, so if C is a fully faithful frame bicategory, then there exists a double functor, strict double functor, Q, from this cross product of the decorated horizontalization of C by this π2 of indexing that we extracted into the globularly generated pace of C, such that Q is the identity on the frames on the decorated horizontalization of C, and Q is absolutely dense on squares. So Q is surjective on squares. And what we get from that is that if C is a frame bicategory and C is fully faithful, we know that the double category on the left of the theorem, that is of length 1, and we have an absolutely dense double functor from a double category of length 1 into another double category, then the double category on the right will be of length 1. So if C is a fully faithful frame bicategory, then it is of length 1. And the same argument proves that if C is absolutely dense, then it is of length 1. Now, there is a little thing to say about this Q. It seems like it should be an isomorphism. I thought it was an isomorphism for a long time, but it's not. And you can find an example where it's not. And also, this seems like it should say that this cross product is universal in some sense, but I haven't found the exact way in which it is universal.
It's not an isomorphism because there are two things that go to one thing, because it's not onto, or it's not one-to-one.
It's not one-to-one. So you might have different expressions for squares in canonical form in this cross product that express the same square, but or that are different squares, but under Q they go to the same square, or in C they are the same. So it just feels very universal E, very free E, this cross product, and this is sort of very much expressed in terms of the Q, and also very much expressed in the fact that the Q is not an isomorphism, and I have an example of this. So this is actually a very easy example. It's span star. In that very easy example, that this is not an isomorphism, and that it just feels like this should be free in some sense, but I haven't found exactly in which sense this is free. But that'll be for another time, for another paper. Yeah. So this is so these are the references for this work, and yeah, that's it.
Thank you very much. Oh, that's a picture of Brooklyn College, of Brooklyn Bridge.
Yep.
Very nice. All right. Thank you. Let's thank the speaker. Everybody put your camera on. Oh, Juan, you might want to shut your slides so that we can see you.
Yep. Just a second. Oh, what is this? I have to go to Zoom.
All right, maybe I can make you an unhost. Oh, there you are. Oh, no.
All right. Okay.
There we are. Thank you very much.
Yeah, thank you.
Any questions? I thought it was very clear. I thought it was it reminds me of, like Ross Street stuff where, showing that all the different whiskering ways somehow work out very nicely.
Yeah. It definitely is like that. Yeah, well, obviously you would never compare it to one of those papers, but yeah, you have to. Well, again, here in the bicategory game, you play the whiskering game. I forgot to mention that. Here, you kind of have to make sure things sort of like the subdivisions kind of work well and they kind of fit together. And if you kind of force the structure, then they do, but then you just have to make it as minimal as you can, and you want to make that a universal thing. But yeah, that's basically what we're doing.
Very nice, very nice. Thank you. Any questions? If not, anyways, thank you. Thank you, Juan. You come back again and fill us in. It's very nice.
Thank you.
Next week, Ray is talking, and we're going to meet in person, right, Ray?
Right. Yes.
Right. So we're looking forward to
my notes ready and look forward to seeing you all in a week.
Right. So Ray's going to talk about retrodiction. I think I'm saying it right.
Yeah.
Right. Anyways, which is a result from. Anyways, very nice. Okay. Thank you very much, everybody. Thank you for showing up. Juan, thank you for giving a wonderfully clear, intelligible talk. It was very nice, very interesting. Thank you.
Thank you so much. And thank you very much for the questions. They were very nice.
Okay, take care. Good night, everybody.
Good night. Thank you.